Right, welcome to question 5 of the Year 10 end of year exam. Some students investigate the energy changes occurring in the reaction between potassium hydrogen carbonate and hydrochloric acid. The equation for the reaction is this. Right. Oh look, a gas has been given off again. I wonder if that'll be important. Maybe not. This is the method used. Measure 15 cm cubed of hydrochloric acid into a glass beaker. Measure the temperature of the hydrochloric acid, that gives us our start temp. Measure a given mass of potassium hydrogen carbonate. So it sounds as if we're a given mass, sounds like we're varying the mass of hydrogen carbonate. Add the potassium hydrogen carbonate to the hydrochloric acid. Stir until all the potassium hydrogen carbonate has reacted. Record the lowest temperature reached. Repeat 3 more times using the same mass of potassium hydrogen carbonate. Each student used a different mass of potassium hydrogen carbonate. Okay, so with a few exceptions, this is almost exactly the same as the experiment we did as our required practical. As a class, we're all using different masses of a solid reacting with a solution to produce a temperature change. They're doing it in a glass beaker, which is different to the way we did it. We did it in a polystyrene cup. What else is different? Well, they used a start temperature and an end temperature, but look, record the lowest temperature given. So what kind of reaction is this? The temperature is going down. The temperature of the system is going down, so it's an endothermic reaction. It's taking in heat from the surroundings, and we are measuring how much heat is being taken in from the surroundings. And they're seeing how, when they change the mass of potassium hydrogen carbonate, how does the change in temperature, the lowest temperature reach? How does that change? Now going to the questions. The method described will not give very accurate results. Suggest one change to the apparatus that would improve the accuracy of the results. Give a reason for your answer. Well, in any experiment when we're talking about measuring temperature change, it's important that we don't let heat to enter or leave the system that we're measuring. So our problem here is we're not using an insulating glass beaker. So the change to the apparatus would be to well, actually I've not answered that question very well, have I? I put beaker is not insulated. Suggest one change to the apparatus would not be that, you idiot. Use an insulated beaker. Use an insulated beaker for a mark, but there's 2 marks. What's the other mark for? Give a reason for your answer. Now this is where 99% of people will fall down, because they're expecting it to do just like most reactions to give out heat. But you've been told record the lowest temperature reached, so it's an endothermic reaction, so heat's being taken in. So we don't want heat from the surroundings to be taken in. Any heat, if I've got my beaker here, this is the system that I'm measuring in here, if the temperature of this is going down, the temperature, if I allow heat in from the outside, this temperature won't go down as much. So I want to avoid heat moving into the beaker. So the problem is heat energy will move into the beaker from the surroundings because there's not an insulator. I need a barrier, I need an insulating barrier to stop heat getting in. So use an insulated beaker, it will prevent heat energy moving into the beaker from the surroundings. God. That was a nasty little trip hazard they put in there for you, which most people unfortunately did trip over. The students controlled the volume of the hydrochloric acid. Give one other control variable the students use. So as soon as we're talking about variables, we're going to remind ourselves of SID, SAM, controlled, we keep the same, independent, we alter, dependent, we measure. So very quickly, let's think, what are our variables here? What are we altering? Well, we're altering, each student used a different mass of potassium hydrogen carbonate. So our independent variable is mass. What are we measuring? Well, we're measuring the lowest temperature reached, the temperature decrease. So our dependent is temperature. Everything else, in theory, is a control variable. We want to keep everything else the same. Now, you are told they kept the same the volume of the hydrochloric acid. Now we know solutions have two important quantities. We have the concentration, the volume, and the concentration. It would be no good using the same volume of a weak acid and then use the same volume as of a scrub that. It would be no good using a volume of a low concentration acid and then keeping the volume same but using a high concentration. Here's the low concentration of the acid, small amount of acid particles in it. Here's a high concentration, same volume, lots of acid particles. So I could keep the volume the same, but if I didn't keep the concentration the same, I wouldn't be keeping the number of acid particles the same, which is the key thing. It's the acid particles that are doing all the reacting, so the number of acid particles is the thing I've got to keep the same. Part of keeping it the same is the volume, the other part of it is the concentration. So the concentration of hydrochloric acid was really the only other answer allowed there. Yes, other control variables, I use the same experimental method, but that's never going to be good enough to earn you a mark, I'm afraid. Then we get into the results. They do 4 trials by the looks of it. Oh look, it's one student's result. So this is one set of results for one particular mass. So this is keeping the mass the same and they're repeating it 4 times. Initial temperature, look, was 21.2, 21.1, 21.0, 21.1, pretty much all the same. The final temperature, 15.6, 15.4, 15.6, 16.6. Right, okay, that one looks a bit of an outlier. Temperature decrease is this minus this, 5.6, 5.7, 5.4, 4.5. That looks to me like an anomalous result. I wonder if they'll ask us about anomalous results. Calculate the mean temperature decrease, mean means average, for the results shown in table 3. Ignore any anomalous results, there it is. Okay, so let's ignore that. Now we're just going to form a mean and give the uncertainty. There's 3 marks for the answer, and the first mark is for saying 5.6 plus 5.7 plus 5.4 divided by 3 gives an answer of 5.566 recurring. It says give your answer to 1 decimal place. Okay, so here's my 1 dp. Then I look at the second dp. Is it above 5? Is it 5 or above? Yes, it is. So that means that number's got to go up by 1. So my mean is 5.6. And then it says give the uncertainty in your answer. Now we haven't done much about uncertainty, for which I apologise, but uncertainty is this. When you form a mean, here it is, 5.6. The uncertainty is the difference between the mean and the furthest result away from the mean. So we've got to look at all our results now. 5.6 is our mean and 5.6, there's no difference. 5.6 and 5.7, there's a difference of 0.1. That could be our uncertainty. 5.6 and 5.4, the difference is 0.2. The biggest difference is the uncertainty. So our uncertainty is plus or minus 0.2. Figure 4 shows the students' results. So look, you see, English, eh? One student, many students. So these are the results of many students. These are the class's results. Thank you, AQA GCSE Board. You couldn't have made that clearer. Well done, you. Draw two intersecting lines, straight lines of best fit. Right, they've told you exactly what to do here. You need 2 intersecting straight lines of best fit. Right, 2 means 2. Intersecting means they cross over one another or they meet. They have an intersection point. That's what an intersection is. A road intersection is when 2 roads meet. Intersecting lines, you know this from maths. Straight means not curvy. Best fit means ignore the anomalous results. So, using your ruler, you would find you could draw a straight line to there, and then a straight line from there to there. Now, can I legitimately include 0, 0? Yes, I can, because when no mass of potassium hydrocarbonate is added, I won't get a temperature decrease. So I can legitimately go to 0, 0. However, I need to stop at this point, because if I draw the line any further on, I'm saying that there is a relationship. I'm extrapolating a relationship up here but I can see that the relationship changes at this point. This is the new relationship. From here to here, that's a straight line proportional relationship, but at here it changes and it goes from there. So I mustn't extend my line that way. And likewise, if I extended this line that way, I'd be saying that this relationship goes that way. It doesn't. The relationship there from 0 to 5 is on this line, and the relationship 5 to 8 is on this line. So there were 2 marks for following the instructions and then realising that if you extrapolate, we extrapolated here, but we know that was fine. We mustn't extrapolate here and we mustn't extrapolate there. Extrapolate means go beyond the data. Explain why the graph has this shape for 3 marks. Use data from the graph. Use data from the graph. So your answer's got to use data from the graph, otherwise you're not bringing those marks home. Let's look at the graph. So we can say between 0, this is our dependent, this is our independent, this is what we're altering the mass, and this is the change that happens, this is the dependent. Changing this makes the change in this. This causes the change in that. So, as we go from 0 to 5, as we increase the mass of potassium hydrogen carbonate from 0 to 5, the mean temperature decrease increases. Right? As we go 0 to 1, it goes from 0 to 1 and a bit. 0 to 2 goes from 0 to 2.5. Yeah, I'm labouring the point. So how are we going to say that? We're going to say as the mass of potassium hydrogen carbonate, look, I used the formula because that's what formulas are for, increases 0 to 5 grams. As I go this way, 0 to 5 grams, using data from the graph, the mean temperature decrease increases from 0 to 6.4 degrees. So here's 0, and here at 5, I'm reading across, that is 6.4. So I've used data from the graph and I've described this part of the line. At 5 grams of KHCO3, so at this point here, increasing the mass of hydrogen carbonate, so increasing it from 5 to 6, has no effect on the mean temperature decrease. Increasing it 6 to 7 has no effect on the mean temperature decrease. 7 to 8, no effect, no mean temperature decrease change. So at 5 grams of KHCO3, increasing the mass of KHCO3 has no effect on the mean temperature decrease. Right? 2 marks, we've explained the 2 lines. Now we need to go in for why. Cheeky because. Okay, because, right? Well, why are we getting no more mean temperature decrease? We're not getting a mean temperature decrease is because there's no more extra reaction happening. As we add potassium hydrogen carbonate here, we get more of a reaction. The more reaction produces more heat taken in. It's an endothermic reaction, so it produces a bigger temperature change. As I add more, I have more of a reaction, so I've got a bigger temperature decrease. But at this point here, it doesn't matter how much more hydrogen carbonate I add, I don't get a bigger temperature decrease because I don't get more reaction. Why don't I get more reaction? Well, it's because I've now got an excess of potassium hydrogen carbonate. There is more potassium hydrogen carbonate than there is HCl, hydrochloric acid, to react. The hydrochloric acid has run out at this point. There is no more. 5 grams of HCO3 reacts with all of the acid. There's no more acid left to react with, so it doesn't matter how much hydrogen carbonate I put in, no more reaction can take place. So I could say it like that, because the potassium hydrogen carbonate is now in excess, or I could say all the acid has reacted, or I could say the acid is now the limiting reagent. Any one of those 3 would be good enough for the final mark.